بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. طلاب المرحلة الأولى إن شاء الله زينين. نبدأ محاضرتنا لهذا اليوم، محاضرة بعنوان Lecture 3. This is Lecture 3 Subspaces. Subspaces فضاءات الجزئية. ابتداء definition، تعريف الفضاءات الجزئية. ناخذ تعريف، هذا أيضا تعريف مهم. Let V be a vector space if W subset of V such that W is a vector space such that W is a vector space with respect to operations of V restricted يعني تقيد restricted to W, then we say that W is a subspace of V, and we write W subspace of V. This is subspace. This is page number 1. And now we take examples about subspace. Example 1. Let V be a vector space notice that V is a subset of V. Of course, V always subset of V, and obviously and obviously V is a vector space. With respect to its operations. Therefore, V is a subspace of V by definition. Likewise, the set containing the zero vector zero is a subspace of V. Notice that zero plus zero equals to zero, and C dot zero equal zero. So axioms A9 and A10 are satisfied. And of course, we can satisfy axioms A1 till A8, A10, because A9 and A10, of course, and this is satisfied. We need just satisfy A1 until A8. Of course, this satisfied. This is satisfied because A1 0 plus 0 equals 0 plus 0. This is commutative. This is, and this is here. Move this here and move this here, the same will be the same. So this is satisfied. And A2, of course, associative 0 plus 0 plus 0. This is, if we are move, this is brackets here, of course, will be the same. And so on. So A1 until A8 are satisfied. This is page number 2. The subspace subspaces 0 is called the trivial subspace. It's called the trivial subspace. Example 2. Let L is equal to x, y. All of the pair x, y belongs to R2, such that AX plus BY equal to 0. Define addition. Define addition and scalar multiplication by the natural rules in R2. Note, if xy zw belongs to L, then x, y plus zw is equal to x plus z, y plus w. And A x plus z plus b plus y plus w, because this is definition. How I know this is will belongs to L? This sum of two vectors will be in the same vector. It will be belongs to L. How I know? So I have to show that this is equal to 0. If I prove A x plus y, A, this is first argument, plus B, second argument. If I prove this is will be equal to 0, so this is will be belongs to L, because this is by definition AX first argument plus B second argument y equal to 0. If this is equal to 0, so this is will belong to L. Now I have to show this belongs to L. So I have to show that A multiply first argument plus B multiply second argument equal to 0. Now I can distribute A here, AX plus AZ, and also this is BY plus BW, and this is will be AX plus BY, move, this is move here, and this is move here, plus AZ plus BW. And of course XY belongs to L, so AX plus BY is equal to 0. This is equal to 0, AX plus BY. And also ZW belongs to L, also ZW belongs to L, so AZ plus BW equal to 0. So now we can see that this is of course equal to 0 belongs Z, because ZW belongs to L. So the AZ plus BW equal to 0 by definition of the set of L, and this is 0 plus 0 is equal to 0. So that's all. And hence x y plus zw belongs to L. This is A9. This is page number 3. And now likewise, if C belongs to R and XY belongs to L, XY belongs to L, that means then AX plus BY is equal to 0. Is equal to 0. If I multiply this equation by C, if I multiply this equation by C, we can get CAX plus CBY equal to 0. Thus x CX, this is CX, because this is will be equivalent to ACX plus BCY is equal to 0. Thus CX brackets CY is equal to CXY. This will be belong to L because satisfy this condition. A multiplied by this CX, B multiply CY, so CX CY belongs to L, and CY CX equal to CXY. So A9 and A10 are satisfied. And the other eight axioms are naturally inherited from R2. This makes L a subspace of R2. we can write L is a subspace of R2. So this is clear. Now this is page number 4. Examples, more examples, because this is important. Examples. If V is equal to R3, now in R3, then number 1, the set 0, 0, 0, this is set, is a subspace of R3. The set is a subspace of R3. Number 2, any line through the origin is a subspace. Number 3, any plane يعني مستوي through the origin is a subspace. From R3, of course. Subspace from what? From R3. From R, subspace from R3. Example 4. Let W is equal to X, Y, Z such that X plus Y plus Z is equal to 1. Is W a subspace of R3? The answer is no. It is not subspace. Now we will explain why this is not subspace of R3. There are many reasons. There are many reasons. First one, 0, 0, 0 doesn't belongs to W. Why? Because 0 plus this is first one, this is plus this is second one, and this is third one, plus 0 equal to 0. But here in the definition of W, X plus Y plus Z equal what? Equal 1, and here equals 0. So this is 0, 0, 0 doesn't belongs to W, because the sum of all arguments will be 0, And here, by definition, W, the sum of all arguments equal to 1. So this is not not belongs to W. Thus, W has no zero vector. Axiom A3 fails. Axiom A3 doesn't satisfy because vector space has to have a zero vector, and zero vector sum with any vector will be the same vector, x plus 0 equal to 0 for all. If there is no zero vector, so A3 will be fail. And this is page number 5. This is page number 5. And this is first reason. And this is enough to say this set is not subspace of R3. This is enough. But also we have other reasons to say this set is not subspace. The second reason, the second reason, let UVW belongs to also A, B, C belongs to the set W. Then U, this is first one, this is plus V plus W equal to 1, and A plus B plus C equal to 1, also equal to 1. And if we sum this one with this one, will be U V W plus A B C. This is will be equal to this is will be equal to U plus A V plus B W plus C. And if we want to say this is vector belongs to W, we have to sum all brackets and we get this sum is 1, because this is by definition of W. Here we define W, first one plus second one plus third one equal to 1, and we have to sum this one plus this one plus this one equal to 1, and see if equal 1 or not. Now this is equal to U plus A plus, this is not equal, we get this is plus this is plus this is W plus C. This is will be equal, this is will be of course equal U plus V plus W. Move V here and move W here, and move A here, A, and move B here, plus B plus C. This is equal 1 here, from here. This is U plus V plus W equal what? Equal 1. And this is plus, this is A plus B plus C also equal to 1. And so this is equal to 2. So this is sum of all arguments equal to, but in definition of W, sum of all brackets will be equal to 1. So this is doesn't belongs to W. Hence U plus V UVW plus ABC doesn't belongs to W. Doesn't belongs to W. That mean axioms A10 fails. So this is second reason why this is not subspace. And the third reason that UVW belongs to the set W, then notice that two UVW equal to 2U 2V 2W. Observe that we sum this is 2U plus 2V plus 2W is equal to 2U plus V plus W, and this is equal to 1 because this is belongs to W, so this is equal to, because this is equal to 1. This is equal to 1, and this 1 to 1 will be 2. Hence 2U 2V 2W will not belongs to W. Thus axiom A9, this is A9, this is A9, this is axiom A9, and this is axiom A10 fails. And this is page number 6. And this we call the subset, the subset W is not closed under scalar multiplication. It's not closed under scalar multiplication. What mean closed? Closed, if I multiply any scalar with vector, will be belongs to this set. If this belongs to, if this vector C X will be belongs to W will be closed. If doesn't belong, so we say this is not closed. Also, this is here. Here we can say we say the addition is not closed. The addition, you can here write the addition is not closed. We say W is not closed under addition. W is not closed under addition, because if we sum two vectors, the result is not belong to W, so this is not closed. If we sum any two vectors, the result will be in the set, will be this set. This set is closed under addition. Now, for this reasons, we say now we can say, of course, one reason is all it takes. One reason enough to say this set is not subspace. Just one is enough, but we explain all. Now we take this theorem. This is important theorem. Let V be a vector space and suppose W is a subset of V with, this is important condition, W is not empty set. W is not empty set. Then W is a subspace of V if and only if the following two conditions hold true. Number one, if xy belongs to W, then x plus y belongs to W. We say W is closed under addition. And number two, if x belongs to W and C belongs to R, then Cx belongs to W. Then Cx belongs to W, and we say W is closed under scalar multiplication. And this is page number 7. Now this is finish theorem. Look at this theorem. Let V be a vector space, and suppose that W subset of V. W now is any subset. This is the first condition. This is also important condition. W is not empty set. Has to have at least one vector. This is not empty set. Then W is a subspace. Here this is symbol of subspace. W of subspace is a subspace of V if and only if the following two conditions hold true. If xy belongs to W, then x plus y belongs to W. This is A9. This is axiom A9. And if x belongs to W and c belongs to R, then cx belongs to W. W is closed under, of course, this is also A10. This is A10 and this is A9. So if a subset, non-empty subset of V satisfy just A9 and A10, just not all, not from A1, A2, A3 until A10, just A9 and A10, so we can say this set is a subspace of V, of space. We can say this is a subspace of V. Now we take a proof of this theorem. Prove this direction. If W a subspace of V, then W is a vector space then W is a vector space with respect to the operation of addition and scalar multiplication. And the scalar multiplication. Thus, one and two and above, I mean this is 1 and 2 in theorem. This is 1 and this is 2. If W is a subspace of V, then the W is a vector space. Then W is a vector space with respect to the operations of addition and scalar multiplication. Of addition and scalar multiplication. Thus all axioms A1 until A10 satisfy. In this theorem we need just A1, A2, so A10 and A9, so 1, 2 are satisfied. Not but just this. and but not just this, but all of them, A1 until A10, are satisfied. So this is the first direction, and the second direction, this is the second direction. Suppose W is non-empty set which is closed under vector addition and scalar multiplication of V now we have to prove that W is a vector space. With respect the operations, with respect the operations inherited from V. So now we have to satisfy A1 until A8. This is page number 8. Now we say let X, Y, Z belongs to W. Then without brackets, X, Y belongs to W, then X, Y, Z belongs to V, because W is a subset of V. So if these vectors in W, of course, will be these vectors in W. Now use A1 and A2 for V. This is, you will be use A1 and A2 for V, not for W. And take this is in W and this is of course in V. So we to find X plus Y is equal to Y plus X, and X plus Y plus Z is equal to X plus Y plus Z. Thus, A1 and A2 hold for W. And now by above theorem, we take it in the previous lecture by 3 of above theorem. We take it in the last lecture. We know that minus 1 dot x equal to minus x, and minus x belongs to w. Why this will be belongs to w. Minus x belongs to w. Why? Because second condition in the theorem, this is second condition, scalar multiplication closed, cx belongs to w, and this is minus 1 belongs to r and x belongs to w, so cx belongs to w, so this is in r, this is in w, so minus x will be belongs to w. Look here, and this is enough to say that minus x will belongs to w, since we know w is a closed under scalar multiplication. And of course also x plus minus x is equal to 0 belongs to w. Why? Because in the theorem, number 1, x, y belongs to w, so x plus y belongs to w. So here x belongs to w, and minus x belongs to w here, minus x belongs to w, so the sum of them equals 0 belongs to w by 1. That A9. That mean A9. This mean A9. And now why? Since w is closed and addition. W is closed under addition. It follows A3 is true for W. Then by arguments just given A4 is true for W. Now this is page 9. Let A, B belongs to R. And notice that by A5, A6, A7, A8, for V we find one dot x is equal to x. AB dot x is equal to A dot B dot x. A dot x plus y is equal to A dot x plus A dot y, and of course A plus B dot x is equal to A dot x plus B dot x. Thus A5, A6, A7, A8 hold true for W. Finally, we assumed closure of addition and scalar multiplication on W. So A9 and A10 are satisfied. Right. And we conclude that W is a vector space. Could satisfy all axioms of vector space. Thus, W is a subspace of V. And since this is finish of proof, the proof is finished, and this is page number 10. And now finish our lectures, because this is clear. This is clear. This is A5, A6, A7, A8 satisfy for V, and we take this is in R, this is in W, so this is vectors X, Y, Z belongs to W, also belongs to V. So this is satisfy for V, all axioms. A5, this is A5. This is A6, and this is A7, and this is A8. This is satisfied for V, and consequently this is satisfied hold true for W, because this is vectors belongs to W. Finally, and we assume this is true, 1 and 2 true, so this is A9, A10, of course true. So we conclude that W is a vector space of V. This is enough. Good luck. Assalamu alaikum wa rahmatullahi wa barakatuh.